Hello and welcome to the eMath Instruction Geometry Regents Review for the New York State Geometry Regents exam. Hi, my name is Kirk Weiler, and for the next 3 hours we're going to be going through old New York State Geometry Regents questions. Used to be called the Common Core Geometry Regents, it's now just called the Geometry Regents, but whatever. The questions are still good. We're going to be going through them for 3 hours. If you want a copy of the questions, you can go over to our site, emathinstruction.com, right up there. Go to our forum page, and the first article on the forum is on the questions that we're going to be using for this and the other presentations. All right, so this morning, Algebra 1 kids, or late morning, early afternoon, Algebra 1 kids took their Regents exam. This Friday, we've got geometry students in the morning and Algebra 2 students in the evening, or in the afternoon, hopefully not in the evening. Tomorrow night, we're going to be doing the Algebra 2 review, so for those of you that are tuning in for the Algebra 2 review, you're one night too early. Anyway, regardless of all of that, let's jump in and start to do some geometry. Okay. Where's my pen? Here it is. Got it. So let's begin by talking about rigid motion transformations and congruency. That's a lot of fancy terminology. But let's begin by just talking about a very simple idea, right? We have objects in two-dimensional space. And when I talk about an object, I could be talking about a line segment. I could be talking about a triangle. I could be talking about a parallelogram, any random shape, any random geometric object, including angles, rays, lines, etc. Sometimes we take a geometric object and we map it somewhere else in the plane. And in that mapping, sometimes the size changes, sometimes the shape changes, but sometimes nothing at all changes except for the location and possibly the orientation of the object. When that happens, what we have are rigid motions, sometimes called rigid body motions. All right? And there's really three of them that you need to know about. One being a translation, also known as a shift, when we take an object and we just slide it a certain distance in a certain direction. Another one is a reflection in a line, when we take an object and we flip it over a line so that it ends up the same distance on the other side of the line as it did on the original, right, giving us a mirror reflection. And finally, a rotation, where we take all the points on an object and we rotate them about some center point by some particular angle. All right? Now, the key is, right, the key with rigid body motions is that all of them preserve what's known as congruency. Two figures are congruent if they are identical in both shape and size. And in geometry, what you learned was that if there's a rigid body motion that will map one object on top of another, then the two must be congruent. So let's jump into some problems that have to do with rigid body motions and congruency. Our first problem of the review, June 2015. The vertices of triangle JKL have coordinates 5, 1 at J, K at -2, -3, and L at -4, 1. Under which transformation is the image triangle J', K', L' not congruent to triangle JKL? All right, so this is very, very important. I'm looking for which of these four transformations will not cause the image triangle to be congruent to the original. Now, one of the interesting things about this problem is that they give you some information that is just wholly irrelevant, which is the coordinates of the three vertices of the triangle. But let's look at the four choices, right? Choice 1 is a translation by 2 units to the right and 2 units down. Again, I don't care how far you translate it. The fact that it's a translation means that the image is congruent to the original one because a translation is a rigid body motion. Number 2, right? A counterclockwise rotation by 180 degrees around the origin. Again, I don't care what point you're rotating about. I don't care what angle you're rotating it through. A rotation is a rigid body motion, so the original and the image are going to be congruent. Number 3, a reflection over the x-axis. Same song, third verse. A reflection is simply a rigid body motion. It doesn't matter which line you reflect it across. The image triangle will be congruent to the original. So the correct choice is going to be number 4, a dilation with a scale factor of 2 centered at the origin. We'll talk a lot more about dilations later, but generally speaking, when you have a dilation, you're enlarging or you're shrinking a geometric object by a set factor so that it retains the same shape, but it's a different size. You've put it on a photocopy machine and you've enlarged it. Or even better, you've taken a photo on your camera and then you've sort of enlarged it or you've shrunk it down. Okay, so choice 4. Let's move on to the next question on rigid body motions. June 2015, number 4. In the diagram below, congruent figures 1, 2, and 3 are drawn. Which sequence of transformations maps figure 1 onto figure 2, and then figure 2 onto figure 3? All right, so let's take a look. Hopefully it's pretty obvious, what we have to do to map this hexagon onto this hexagon. But here's the cool thing, right? If I take point A and I sort of like draw a vector or a ray to A prime, and I do the same thing for B, or at least I try, notice that those two rays or vectors are the same length and they're parallel to one another. That means all I've done is a translation. I've simply taken this in this direction, each one of the points. So let's see, that eliminates 1 and 2. We begin with a translation followed by something else. Now choice 3 says followed by a reflection. Choice 4 says followed by a rotation. And it's a little tricky because they both seem like they could be correct. Possibly I've rotated this thing 90 degrees clockwise about the origin, or maybe I've like reflected it across some line like y equals x. So which one is it? Well, it turns out that it's a rotation, and here's how I can tell. Let me get rid of these lines so we can see it a little bit better. When we take a look at this hexagon and we look at A prime, B prime, C prime, D prime, etc., to go in alphabetical order, we would have to go around the hexagon clockwise. Notice down here, if I look at A double prime, B double prime, C double prime, etc., I also go around the hexagon clockwise. Whenever you reflect an object across a line, what happens is the orientation of the letters literally reverses itself. So had this been a translation followed by a reflection, we would have then expected to see these image points go counterclockwise around the hexagon, but because they're still going clockwise, it must have been a rotation and not a reflection. All right, and in fact it was a rotation by 90 degrees about the origin, clockwise. All right, let's keep going. January 2016, number 11. Quadrilateral ABCD is graphed on the set of axes below. When ABCD is rotated by 90 degrees in a counterclockwise direction about the origin, its image is quadrilateral A prime, B prime, C prime, D prime. Is distance preserved under this rotation? And which coordinates are correct for the given vertex? So, let's first talk about the first question. Is distance preserved under this rotation? Well, the whole point of a rigid body motion is that distance is preserved as well as angles. So the fact that it's a rotation means that distance is automatically preserved, meaning that the distance between A and B will be the same as the distance between A prime and B prime once we've rotated it. So the first answer is yes, which means if we're just doing some test-taking strategies, we can eliminate choices 1 and 2 because they have no. Now the question is, which one of these is correct? It's extremely important. We have a 90-degree counterclockwise rotation, counterclockwise. The best way to do this, strangely enough, is to just take your test paper and rotate it 90 degrees counterclockwise. So I take my test paper, I rotate it 90 degrees counterclockwise, and I start reading off now the coordinates. So for instance, A prime now is going to be negative 1, 2, 3, 4, 5, 6, negative 6, negative 2. B prime is going to be 1, 2, 3, negative 3, positive 1, 2, 3, 4. All right, I'm going to rotate that back clockwise again so I can get it like that. Now, I could have also written down the image coordinates of C prime and D prime, but the plain fact is, since these two choices only involve A prime and B prime, I just have to take a look. This one says 6, 2. Well, that's not where A prime ended up. A prime ended up at -6, -2. But B prime at -3, 4 is exactly what we have there. Now, you really have to watch out for this one, because if you took this thing and you rotated it 90 degrees, but you went clockwise, then A prime would appear to be at 6, 2, and that would be choice 3. They're trying to pull you into that one, right, by saying, well, you know, one of the likely mistakes they're going to make is to rotate clockwise instead of counterclockwise, so let's come up with an answer that reflects that mistake, and that's choice 3. Watch out for stuff like that. Okay, let's keep going. Hopefully, let's keep going. All right, so finally we have a free response question. January 2016, number 28. Let's read it through. As graphed on the set of axes below, triangle A prime, B prime, C prime is the image of triangle ABC after a sequence of transformations. A sequence of transformations. In other words, there's going to be 2 or more transformations that it's going to take to map ABC to where it ends up A prime, B prime, C prime. The question is a triangle A prime, B prime, C prime congruent to triangle ABC? Use the properties of rigid motion to explain your answer. All right, so let's talk about it. So the first thing that we want to do in a situation like this is actually figure out what the sequence of transformations is that will map ABC to where A prime, B prime, C prime is. All right, well, honestly, there's a lot of different transformations that would work. All right, one thing that we could do is we could actually shift the entire triangle down by 3 units. All right, just a vertical translation. Right? And then what we could do is we could then take that and reflect it across the y-axis so that it lands on A prime, B prime, C prime. Likewise, we could start by reflecting it across the y-axis and then shifting it down 3 units. Both of those sequences would actually get the job done. So, the first thing I'm going to say is that triangle A prime, B prime, C prime is the image of triangle ABC after a translation. Watch out, it's easy to confuse the word translation with transformation. A translation and a reflection. Since both are rigid motions that preserve, we're going to talk about that word a little bit more, preserve shape and size, the 2 triangles are congruent. I think that's already more writing than I did last night for the Algebra 1 review. All right, so let's talk about this answer a little bit. A prime, B prime, C prime is the image of triangle ABC after a translation and a reflection. All right, I don't really have to get into what the exact translation is, what the exact reflection is. But since both are rigid motions that preserve the shape and the size, right? Properties of rigid motions, we have to mention that, right? Then the 2 triangles are congruent. This word is a great one to use anytime you have to discuss the properties of rigid motions. Rigid motions preserve distance, which means they preserve size, and they preserve angle measurements, which means they preserve shape. All right? So, we'll look at dilations later where the angle measurements, stay the same, but the sizes change, all right? But preserve means it doesn't change, right? Things stay the same. If A and B are 3 inches apart, then when they get transformed using a rigid motion, A prime and B prime are also 3 inches apart. Okay? And the final one. This is a really well-designed question. Okay, so let's do one last one. Now, before we get into this, a couple announcements that I probably should have made right at the beginning. Okay, but now is as good of a time as any. I'd like to remind people that we're going out live tonight on both the Kirk Weiler YouTube channel, Kirk Weiler, the Kirk Weiler YouTube channel, and Instagram at eMath Instruction. Now, if you're watching the live feed on Instagram, that's great. You know, you're getting the entire thing, but the video quality and the sound quality, and that's a big piece of it, is much, much better on YouTube. So we would definitely recommend that you go over to YouTube. Now, don't get me wrong, go ahead, view on Instagram, that's great. You get to see me wearing my sandals. Awesome. But you're going to get to see me drink lemonade either way. In fact, why not take a break for lemonade?
Some of the Instagram people say it's hard to see the screen.
So apparently we're getting feedback that the Instagram viewers are having a hard time seeing the screen. Now again, one of the great advantages of going over to YouTube is that we keep cutting back and forth between the screen and myself, and that way when I'm writing on the screen, you don't have to look at me and my back and my head, right? You're just watching the writing magically occur on the screen. Another announcement, every hour Instagram cuts out, so we have to stop the Instagram feed at that point. Last night in Algebra 1, we just kept the YouTube stream going, but we found as the night went on, the video tended to get a little bit more choppy. I don't know why. It could be the computer overheating, who knows. So what we're going to be doing is we're also going to be stopping the YouTube feed every hour on the hour, but then we're going to be picking it right back up, okay? So don't worry, if we've got to stop the video every hour, please come back, join us again. Let's keep going. August 2015, number 34. All right, in the diagram below, segment AC is congruent to segment DF. And they've marked that nicely for us. And points A, C, D, and F are collinear, meaning that they all lie on the same line, and in fact, they all lie on line L. Let triangle D', E', F' be the image of triangle DEF after a translation along L, such that point D is mapped to point A. Determine and state the location of F'. Explain your answer. All right, so let's talk about this a little bit. So first off, translations, right? What that means is I'm going to take this triangle and I'm just going to shift it along this line. Okay, the line is sort of dictating the direction that I'm going in. But the distance I'm going is such that point D gets mapped all the way here. So this is where D' ends up. What they want to know is where F' ends up. Well, as you can probably guess, because we're translating all of them the same direction and the same distance, F' ends up at C. All right, we've got to talk about why. Now, a really nice way of doing that is F gets mapped to point C. Okay? Now, why does that happen, right? It happens for two reasons. One reason is random red. This happens because a translation is a rigid motion that preserves distance and here's the kicker, and it's very important, AC was congruent to DF. All right, so let's talk about this a little bit. This is really important to understand why the two things are important, right? So number one, it's important in this case that when we translate segment DF along this line, it doesn't suddenly get smaller. It doesn't shrink, it doesn't enlarge, and it's just taking this whole segment and going whoop like this. The other piece that's really important is that this segment and this segment were the same length to begin with. Therefore, as I slide this along, when D gets mapped here to point A, then F must get mapped to point C. Okay, so both of those are important. The fact that we preserve distance and AC is congruent to DF. If those two things hadn't been the same length, well, then there's no reason F would have been mapped to C. In fact, it couldn't have been mapped to C. Let's take a look at the second part of this problem. I've redrawn the picture here. It says let D double prime, E double prime, F double prime be the image of triangle D prime, E prime, F prime after a reflection across the line L. Suppose that E double prime is located at B. Is triangle DEF congruent to triangle ABC? All right, so this is really cool. Let's come back to this. So, the first thing that we did was we took this triangle in the first part of the problem and we translated it, right? We translated it like this, and it ended up having D prime here, E prime here, and F prime here. All right, they then said we're going to reflect this across line L such that F double prime ends up down here at B, right? And the question now is this new triangle, D double prime, E double prime, F double prime, congruent to the original triangle, DEF. All right, well this is cool. One thing that you'll want to show in this is you'd want to show the fact that D double prime and E double prime just stay right there. And of course they stay right there because they are on the line of reflection. Anytime you reflect a point that sits on the line of reflection, it doesn't go anywhere. It would be like if you're touching a mirror, right, then your finger is sort of touching its image, right? They're in the same place. Now, why would this triangle have to be congruent to this triangle? Well, we have mapped triangle DEF onto triangle ABC using two rigid motions. So the two triangles must be congruent. Right? We've got nice supporting work here, right? We've done the translation. We've done the reflection. We know that D double prime and D prime are in the same place. E double prime and E prime are in the same place. We were told that F double prime got mapped onto B, right? And that means that we've taken this triangle and using a translation and a reflection, we've mapped it onto this triangle. So the two triangles must be congruent because we use two rigid body motions to get there. All right. Oh, a little bit more. June 2018, a little bit more work with just transformations. Problem number 19. The regular pentagon below is rotated about its center. Which angle of rotation will carry the figure onto itself? All right, so whenever we have a regular polygon, okay, and those are things like equilateral triangles, squares, pentagons that have all five sides the same length and all five angles the same, right? Hexagons, same deal. A regular pentagon is a regular polygon is a polygon, right? A straight-sided figure where all the sides are the same length and all the angles are the same. And because of the symmetry that they have, there's always some kind of center. And you can rotate that regular polygon around the center so that it is mapped onto itself. In other words, you rotate it and it lands on itself. Rotate it, lands on itself. Or it rotates and it lands on where it originally was. So the question is, which angle of rotation will carry the figure onto itself? So the way you want to do a problem like this is you want to think about what is the sort of the bare minimum angle that it would take, right? So if you can imagine, right, let's say that this was point A and this was point B. Well, if I rotated so that point A went to point B, then point B would go to point C to point D, etc. The question is, what would that angle be? Well, we can figure that angle out very easily because if we divided up this pentagon into those 5 congruent triangles, we would know that this angle, right, let me call it X, that angle would be 360 degrees divided by 5, which, you take your calculator out and you figure out it's 72 degrees. Now, 72 degrees would be one angle of rotation that would map this figure onto itself. But it's not one of the choices, all right? So what else could be the right answer? Well, you could also rotate 72 and then another 72. So you could rotate 72 times 2, which would be 144 degrees. That is also not a choice, but we could rotate 72, 72, 72. That would be 72 times 3, and that would be 216 degrees. Ah, there it is. All right, so some whole number multiple of that smallest angle will always rotate the figure onto itself, right? 72, 144, 216, the next multiple of 72, etc. And you can always find that for a regular polygon by taking the number of sides, dividing 360 by the number of sides to get that smallest angle of rotation it will take to rotate that figure onto itself. Again, that's for a regular polygon. Let's keep going. I love this question. August of 2018. Problem number 4. In regular hexagon, A, B, C, D, E, F, shown below, A, D, B, E, C, F all intersect at G. Awesome. When triangle ABG is reflected over BG and then rotated 180 degrees about point G, triangle ABG is mapped onto what? Okay, so this is a fun problem. Let's take a look at this. So they're talking about triangle ABG. All right. And what they want us to do, I'm going to draw this in red, is they want us to reflect it across this line, right? So I'm going to take this triangle and I'm going to reflect it across that line, and where it's going to end up is right here, right? You should be able to see that. If I take it and I just reflect it over, it's going to end up there. And then if I rotate this triangle by what? 180 degrees about point G. So I take the triangle up here and I rotate it 180 degrees. I can't really actually do that, but if I rotated it 180 degrees, it would rotate down here, right? And so taking this triangle, reflecting it over here, and rotating it 180 degrees down here would mean that it would map onto triangle FEG. It's kind of a neat problem because it gets to some very basic transformation work. Can you predict where a figure will be mapped to under a couple of rigid motions? In this case, first a reflection and then a rotation. All right, I think that might be it. Not for the whole night, just for the first set of topics, rigid body motions and transformations. Let's see what we have next. Parallel lines. Okay. So first, let's talk about some basic review on parallel lines, right? We all have been seeing parallel lines for a while. These two lines in red are parallel lines, and parallel lines are lines that when extended forever will never intersect, okay? And you really want to think about them as just lines that are they're going in the same direction, right? They're going in the same direction, but they're not the same line. Now, when you take another line and you cross the two parallel lines, that's what's known as a transversal. All right, so this line is called a transversal. So R is a transversal and P is parallel to S. Now when that happens, what happens is 8 different angles are formed. 8 different angles, all right? And these angles have special names, but the two that are really the most important are what are known as corresponding angles and alternate interior angles. Corresponding angles are simply angles that are sort of showing up in the same spot on the cross. In other words, angle 2 and angle 6 correspond, right? Angle 4 and angle 8 correspond. Angle 3 and angle 7 correspond. Angle 1 and angle 5 correspond, right? They are corresponding angles, and corresponding angle pairs are always congruent, or are always congruent when formed by parallel lines and a transversal. Equally important, maybe even a little more important than corresponding angles, are alternate interior angles. You see, when I've got two parallel lines, 4 of the angles formed are on the interior, the inside of the two parallel lines. And alternate angles are on opposite sides of the transversal. 7 and 2 are alternate interior, 8 and 1 are alternate interior, and alternate interior angles are also congruent. Now there's all sorts of other terminology like alternate exterior and same side interior and same side exterior and all sorts of things like that. All right, and most of the time those then are supplementary. They add up to 180 degrees. But most important are the angle pairs that are congruent, and those are corresponding angles and alternate interior. A lot of people like to think about alternate interior angles as being the angles that are created by the z of parallel lines. All right, let's get into some parallel line work. June 2018, 1 year ago today. Now, never forget to have your handy dandy calculator ready and waiting. Maybe have it a little bit closer to you, right? Have your calculator ready, right? Just to do little bits of work here and there, right? So, June 2018, number 2. In the diagram below, AB is parallel to DEF, AE and BD intersect at C, measure of angle B is 43 degrees, measure of angle CEF is 152 degrees. Which statement is true? You know, one of these problems is kind of annoying because, you know, it'd be great if they just were like, hey, what's the measure of angle D? You know what I mean? Then you're like, I'm finding angle D. But no, they're gonna like test us to see which angle we think is right. Well, let's fill in whatever angles we can fill in based on what we know. Well, first thing I can tell you is I can say that since AB is parallel to DEF, if that's 43, this is 43. Those are those alternate interior angles, the angles of the z, so to speak. Now, because this angle is 152 degrees, I can of course take 180, subtract 152, and find out this angle. I can just do a little 180 minus 152, right? And that's going to give me 28 degrees. All right. Now, likewise, right? Think about this. I could now take my 43 and my 28, I could add them together, subtract from 180, and I can find this angle. Because of course, all triangles have their angles summed to 180 degrees. So I do a little bit of 43 plus 28, and I've got 71 degrees. And then I do 180 minus 71, and I get 109 degrees. So that's going to be this angle. All right. So let's start to see, you know, and of course these two, this is going to be 109 degrees because those are vertical angles, right? We're getting a lot of nice review in. And finally, angle A, right, is going to be 28 degrees because that's another kind of Z scenario. So this is going to be 28 degrees. That doesn't look like a 28. Let me try that again. This angle is 28 degrees. All right, let's take a look. First, measure of angle D is 28. No, measure of angle D is 43. So, nope. Measure of angle A is 43. No, measure of angle A is 28. Measure of angle ACD is 71. ACD. What's ACD? Well, ACD is this angle here, right? That's angle ACD. And I haven't actually figured out what that angle is, but this angle is 109 degrees. It may not look like 109 degrees. Maybe go back to the screenshot really quick so that we can take a look. It's just a little bit easier to read, right? So we've got this angle at 109 degrees, right? Which now will let me to calculate the measure of angle ACD. We can simply do, right? We can say measure of angle ACD is going to be 180 minus 109 degrees, which is going to be 71 degrees. I feel like I've seen that before. And that, in fact, is the correct answer, 71 degrees. All right. And it's kind of cool, this problem, because it forces us to think about those alternate interior angles. It forces us to think about the sum of the angles in a triangle being 180, vertical angles being congruent, right? Things like supplementary angles from linear angle pairs, or in other words, angle pairs that form a straight angle. Right? So lots of nice things there, especially with the alternate interior angles. Now, what's kind of interesting about parallel lines is if two lines are parallel, then alternate interior angles are congruent and corresponding angles are congruent. But that's actually a two-way street. And what I mean by that is that if alternate interior angles are congruent, then the lines have to be parallel. Or if corresponding angles are congruent, then the lines have to be parallel. So you can use congruent angles to prove lines are parallel. as well as having parallel lines, prove that angles are congruent. So let's take a look at June 2015. Number 17, Steve drew line segments ABCD, EFG, BF, and CF as shown in the diagram below. Scalene triangle BFC is formed. I don't know why they tell us it's scalene, but whatever. Which statement will allow Steve to prove that ABCD is parallel to EFG? All right, let's take a look. So we want to figure out which one of these angle congruency statements will allow us to say that this line ABCD, or this line segment, is congruent to this line segment EFG. All right, now there are no corresponding angles here, but there are alternate interior angles all over the place. One of the unfortunate things about this problem is that the correct choice is number 1. All right, and that's a little bit annoying because, like, literally when we look at choices, and this is really the kind of problem where you want to go through each choice to figure out which one's correct. Well, the first one's correct. And let's take a look at why. Angle CFG, which is this angle, is congruent to angle FCB, which is this angle. And those are truly those alternate interior angles, right? The alternate interior angles, the forming of the Z. And because those two angles are congruent, that would then be sufficient evidence to show that that line segment and that line segment are parallel. Now, just for a moment, let's take a look at choice 2, one of the wrong choices, because it's kind of interesting to see what wouldn't lead us to that conclusion. I'm going to get rid of this and maybe just go over to red, because this is going to be incorrect. But let's see, choice 2 says angle ABF, that's going to be this angle, is congruent to angle BFC, this angle. All right, now if we knew that these two angles were congruent, number 1, by the way, they don't look congruent. This is an obtuse angle, that's an acute angle. Those two angles can't be congruent. But if for some reason they were, right, what that would show us then would be that this line segment and this line segment are parallel. They're obviously not parallel because that line segment is part of this entire line segment, which is then intersecting this line segment, hence the not parallel piece. But those two are certainly not sufficient to show that those two lines are parallel. Anyway, choice 1 is correct. We could go through the other 2 incorrect choices, but we've got a long way to go tonight and many problems to do. Proofs, constructions, measurement, similarity, dilation, so much to do. June 2015, last problem on this. Number 32, in the diagram below, segment EF intersects segment AB and segment CD at G and H respectively. Ah, isn't this nice? It's all respective. All right, and GI is drawn such that GH is congruent to IH. That's an important piece of information that they've given us here. Important piece of information. If the measure of angle EGB is 50 degrees and the measure of angle DIJ is 115 degrees, explain why AB is parallel to CD. All right. And honestly, and I'm kind of picky about the way tests are constructed, I kind of wish it had said, explain why AB must be parallel to CD. Do you know what I mean? I mean, like, hey, I think AB is parallel to CD because that's the way they were drawn. You know what I mean? Or maybe they could have said, explain why we know that AB is parallel to CD or something like that. Anyway, we're doing whatever. Let's start to throw in the information that they've told us. What do we know? We know that the measure of angle EGB is 50. EGB is 50. So that's this angle up here. We know that the measure of angle DIG is 115 degrees. Very important that you can handle these 3-letter angle statements. All right, we also know that GH is congruent to IH. Okay, so let's come back to it and take a look at what we have so far. There still isn't anything here that would lead me to understand why AB should be parallel to CD. In order to get that, we're going to really need a couple of alternate interior angles to be congruent or a couple of corresponding angles to be congruent. So let's try to start to fill in some other angles. One easy angle that we can fill in is, given that we know that that's 115, we can subtract from 180 and figure out what that angle is. So I do a little 180 degrees minus 115 degrees, and I believe that's 65 degrees. All right, so let me fill it in. Now, here's where it's critical that they told us that this segment and this segment are congruent. That means that this triangle, let me outline it in red, this triangle is an isosceles triangle. Now it's oriented in a little bit of a strange way, right? But it's still an isosceles triangle. Now remember, in an isosceles triangle, the angles that are opposite the two congruent sides have the same measure. Well, that one goes with that 65, and that one means that one's 65. So let's throw a 65 in there. Now we can do one last angle, right? We can add the 65 and the 65 together, or multiply by 2, either way, and we can get 130 degrees. And because those two then add up to 130, we can subtract that from 180 to figure out that angle. I think I can do that without writing it down. 180 minus 130 is 50. Actually, maybe I'll write it down just to be able to show my work. It does say explain, which means we've got to use words, and we're going to get there. All right. This is great. Because notice, I now have a 50-degree angle here and a 50-degree angle here. Now it's a little bit tricky because you want to kind of mentally remove that line segment. And if you sort of kind of mentally remove it, right, then you can really see that the 50 and the 50 are in the same spot, right, in terms of those two lines that are being crossed by a transversal. This angle and this angle are corresponding angles. And because we now have a pair of corresponding angles that are congruent, the two lines that created those corresponding angles must be parallel. So we got to do a little explaining, right? A little explaining. So let's do a little bit of explaining. Give ourselves a little more room. All right. I'm going to say angle EGB and angle GHI are corresponding. It sounds like the clock is ticking. Angle EGB and angle GHI are corresponding and are congruent. So AB must be parallel to CD. All right. Now, of course, one of the things that you're missing if you're watching on YouTube and not Instagram is my producer running in and fixing the tag on my shirt, okay? So the Instagram people, you got to see that. And my samples. They're UFUS, by the way. They're great. And again, I'm not saying that because UFUS is paying me a lot of money. I mean, they are. But that's not why I'm saying it. They're just great samples. They're not paying me any money. I think they're like a Swedish company or something. I mean, who calls this shoe UFUS? Seriously. All right, let's move on. What do we got? Dilations. All right. So dilations are the sort of fourth major type of transformation that you looked at in this course. All right. A dilation can generally be thought of as a transformation that either enlarges an object or shrinks an object, but doesn't change its shape. You know, it just changes the size that it appears to be. But in high school geometry, we took dilations to a whole nother level. We really kind of defined how mathematically dilations work. So let's review that, all right? To begin with, in a dilation, right, you've got 2 points. Let me get rid of this, right? We've got the point that's being dilated, let's say that's point A, and then we've got the center of dilation. All right, and between those 2 points, there's some distance. We call it CA or AC, right? Now, how do you dilate point A about point C by a dilation factor of K? Well, the first thing that you do is you draw a ray starting at C so that it passes through A. So something like that, not something like that. Hey, something like that. That's better. Okay, so we've got this ray CA. Right? And then what happens is we stretch out point A, right, along that ray, or we shrink it back along that ray by a factor of K. But the key is, right, we need the center to sort of say, hey, how far do we move A away from or towards the center? All right, and it's a little weird because we need that center, we really do. And all we do is we take the distance that the point is away from that and we multiply it by some constant. If that constant is greater than 1, then the point A is going to move, A prime is going to move away. And if K is less than 1, right, then A is going to move towards the center. The object's going to get smaller, right? If K is 1/2, then the object looks half as big. All the distances are half the size. Now, that's just how you dilate a single point. But oftentimes what we're doing is we're taking something like a line segment and we're dilating it through a center of C. Now what's really cool is when that happens, right, we do the same thing. We stretch out point A, we stretch out point B, okay, both by that same factor of K, and we produce an image line segment A prime B prime. Now the cool thing about that image line segment is it's got two amazingly important properties, actually even three. Number one, that image line segment is always parallel to the original. And number two, the length of the image line segment has been stretched by the same constant that we use to dilate the 2 points. And that's not immediately or apparently obvious, okay? But it is the case in all dilations. Now, one last little point before we actually get into dilation problems. This is what happens when we take a line segment and we dilate it about a center point that's not on the line segment that we're dilating, right? It's off of it. It's not sitting somewhere on AB. But we should consider that case where we've got, it's somewhere here, there it is, where we've got a line segment, AB, and we've got the center point that's actually on the line segment. Then what happens is, we stretch B out here, we stretch A out here, okay? And then instead of having an image line segment that is parallel to the original, we've got the original actually sitting on the image, and all of them are sort of sitting on the same line. They're collinear, all right? And that's going to pop up. It's not the biggest, most important thing, but we'll see one multiple choice type of problem where this fact comes up, that when you dilate a line segment about a point that lies on the line segment, you're just kind of stretching out that line segment or shrinking it back, but it still sticks on the same line. Anyway, let's jump into some dilation problems. Dilations preserve angle measurements, which means they preserve the shape of an object. Angles don't change, but distances do. January 2017, number 13. On the graph below, point A at 3, 4, and BC with coordinates B, 4, 3, and C, 2, 1 are graphed. All right. What are the coordinates of B prime and C prime after BC undergoes a dilation centered at point A with a scale factor of 2? So this is where it's very, very important that you just didn't do dilations centered at the origin. So it used to be, and I'm sure your teachers didn't do this with you, but it used to be that all we ever did was dilate points with a center at the origin using like graph paper. Now we should be able to dilate them using kind of any random point. Now think about this for a second. Let's take a look at point B. Right, we're going to use A as a center, and we want to stretch B by a factor of 2 away from A. I could use the ruler, but I think I'm going to freehand to save a little bit of time. Literally, right, what we're doing, remember, right, we're drawing that ray out from the center through the point we're dilating. And now we just want to stretch it so that B prime is twice as far away from A as it started. Well, right now it's sort of, if you will, one diagonal unit away. So now if I stretch it out, it's going to end up 2 diagonal units away from A, right? It used to be this, now it's this. All right, now for C, we're going to kind of do the same thing. Right? And this is where a ruler really would come in handy. But again, the idea is if I had to like think about that distance, I could think about it as kind of going 3 down, right? Yeah, 3 down and 1 over. So if I want to reproduce that distance, I'll go 3 down and 1 over, and C prime is going to end up here, right? Now, they never asked me to do it, but I could draw this in. This is kind of a picture you see time and time again. Remember, B prime, C prime is now twice as long as BC, and it's parallel to it. You can kind of see that parallelism. They don't really ask about that. They just want the coordinates of B prime and C prime. That's easy enough, right? B prime is now at 1, 2, 3, 4, 5, 6, 2. Wait, no, 1, 2, 3, 4, 5, 2. So B prime is at 5, 2. And And C prime is now at 1, -2. All right, so where is it? Choice 1. All right, and it's that idea. Here's our center. Here's the point that we're trying to dilate. We draw a ray through it, and then we just make sure that the image point is twice as far from the center as it was to begin with. Now again, that's because we have a dilation with a factor of 2. Everything is getting twice as far from the center of the dilation as where it started. By the way, just one moment, because this sometimes is important. When we dilate everything in the plane, the center of dilation wouldn't go anywhere. It's kind of like when you reflect a point that lies on the line of reflection, right? And it wouldn't go anywhere because the distance it is from itself is 0. So if we multiply that by 2, it's still 0. We're not adding, right? We're multiplying. Anyway, let's keep going with dilations. August 2015, number 18. In the diagram below, CD is the image of AB after a dilation of scale factor K with a center at E. Which ratio is equal to the scale factor K of the dilation? Now, these can be particularly tricky problems because you have to keep your eye on the ball and you have to realize what is the image and what is the pre-image, the original. CD is the image, AB is the original. Really important. CD is the image, AB is the original. Now, I'm going to do something really quick. I'm going to take E and I'm going to connect it to D and B, kind of so I have a similar diagram as what I had before. Now, the reason I'm going to do this is that what I always kind of get in this situation is I get what I would call nestled triangles. I'm going to kind of draw those separate. All right, I get triangle ECD, and I get the bigger triangle. And that's triangle EAB. Now, if you will, this is the original. This is the image. Whenever you're looking for the constant of dilation, you always want to take a length on the image and divide it by a length on the original. Or as I like to think about it, a new length divided by an old length. All right? So for one of the, again, unfortunate things about this problem is that the correct answer is choice 1 again. And let's take a look at that. EC divided by EA. So EC and EA are the corresponding sides on these two similar triangles. We'll talk about similarity more later, but these two triangles are similar. Since this is the image triangle, we can take this length and divide it by this length to figure out the dilation constant. By the way, we could also do this length divided by this length, or we could do this length divided by this length, okay? But none of those are actually choices. And in fact, the one that we really have to worry about is choice 4, all right? Which says EA divided by EC. Choice 4 would be the correct choice if this was the image and this was the original. And very often, when students see a small segment and a large segment and they see a dilation, they think, oh, it's got to be the larger segment, which is the image, and the smaller segment, which is the original. But here, they're very clear. CD is the image of AB. So this thing was the image of this thing. So this smaller triangle, if you will, is the image of this larger triangle after a dilation by K. So always do a new length divided by an old length and get those nestled triangles. And here those nestled triangles are again. August 2015, number 23. In the diagram below, triangle ABE is the image of triangle ACD after a dilation centered at the origin. The coordinates of the vertices are blah de blah. I won't read through them all. We've got them there. The ratio of the lengths of BE to CD is which of the following? All right, so great. This is actually seems on the surface a very straightforward problem. They just want to know the ratio of the length of BE to CD. So, you know, I'm looking for BE divided by CD. The problem with that is, you know, to actually figure out those two lengths, number one, would involve the Pythagorean theorem, which we could do, all right, but they aren't going to be nice. I mean, BE is not bad, all right? It's not too bad, 1, 2, 3, 4, 1, 2, 3, because it's actually got a length of 5. But CD is considerably uglier, specifically because point C has coordinates 4.5, 0. Imagine kind of dealing with that. So just for a moment, what I want to do again, I'm just going to move this up here really quick, because I'd like to draw these two nestled triangles, okay? One of them, the smaller one, right, EAB, and the larger one, all right, is ADC, right? And keep in mind that, if I can get that gone, I'm looking for BE divided by CE. I'm looking for this length divided by this length. Well, the great thing is that BE divided by CD is going to be the same thing as AB divided by AC. So this is also equal to AB divided by AC, and it's also equal to EA divided by AD. Right, that's the whole point. All three sides are dilated by the same constant, and so the ratios of this side to this side is the same as this to this, is the same as this divided by this. Now, are any one of these two easier to find? Well, AB, that's not bad, that's 3. But this is like 4.5, so that's not terrible. I mean, I could do 3 divided by 4.5, but it's a bit ugly. On the other hand, EA, well, this is 4, and AD, this is 6. Well, that's going to be a piece of cake, right? EA divided by AD is just going to be 4 to 6, which is equal to 2/3. Choice 1. So it's kind of cool because at first you kind of look at it and you think, oh yeah, you know, I should do this length divided by this length, except they're diagonals, so they've got kind of ugly lengths. They could involve square roots and things like that, right, due to the Pythagorean theorem, right? And what they're really testing is, do you know that the ratio of this to this is the same as the ratio of this to this? 2/3. All right, let's keep going. All right, August 2016. Here we go, nestled triangles again, triangle, triangle. The image of triangle ABC after a dilation of scale factor K. This is very important. They haven't told us what the scale factor is. They've just said it's scale factor K. Centered at point A is triangle ADE, as shown in the diagram below. Which statement is always, very important, always true? All right. Well, is it always true that when we multiply AB by 2, we'll get AD? Well, it would be true if the scale factor was 2. But we don't know that the scale factor is 2. They've certainly drawn it to make it look that way, but it's always true. Always true. Well, this is only true again if the scale factor has to be 2. All right. Number 2, AD is perpendicular to DE. Well, again, that would be true if we knew that AB was perpendicular to BC. If we knew that, if they told us somewhere up here that AB was perpendicular to BC, then certainly AD would be perpendicular to DE because dilations preserve angles. But we're not told that. So that certainly doesn't have to be true either. Does AC have to be equal to CE? Only if the dilation constant is equal to 2 again. And they didn't tell us that. So we're really left with choice 4, which is a fundamental property of dilations. If I take segment BC and I dilate it and its image is DE, those two segments are going to be parallel to each other. So I could have gotten that right away. How are we doing on time, Joey?
It's time to stop.
Oh, it's time to stop. I just totally lost track of time. I was having so much fun. So we're going to take a brief break, maybe 1 or 2 minutes at most. I'm going to get refreshed and, you know, powder my face and stuff like that. And then we'll be right back on both YouTube and Instagram. See you soon.
Go live here. Okay, this is live. Zoom in.
Hi, and we are back for hour 2 of the Geometry Regents Review. Welcome back, everybody. I hope that you came back to us because we're still working with dilations. All right, we're almost done with them. We're almost done with dilations, and then we get to move on to more fun topics. We haven't even started doing really proof yet. Anyway, January of 2017, problem number 2. In the diagram below, triangle ADE is the image of triangle ABC after a reflection over the line AC, followed by a dilation with the scale factor AE divided by AC centered at point A. All right, they've given us a lot of information here, more information than we really need to know, but they then ask us which of the following statements must be true. So let's think about this for a moment, right? So triangle ADE is the image of triangle ABC after a sequence of transformations. The first one being that we took this thing and we reflected it over. Now for a moment, think about what that would probably look like, right? It kind of look like this. And then we got those like nestled triangles again on this side. And then we took that thing and we dilated it, right? We held A as the center, and then we kind of just moved this thing up to here, and we moved this thing up to here, and we produced then this image triangle ADE after that dilation. Now that being given, I'm gonna just, well, actually, maybe I'll leave that there. All right, what I'll do is I'll now outline ADE in red so that we can really see it. All right, so that's my image triangle. So which of the statements must be true? The measure of angle BAC is equal to the measure of angle AED. All right, that's this angle and this angle. No. How about the measure of angle ABC, that would be this angle, is equal to the measure of angle ADE. That's this angle. And that's actually our winner, all right? I would like to talk about the other two, okay? And I can talk about why this is the right one while also talking about why those are the incorrect ones, all right? This is the right one because both rigid body motions, the reflection, and dilations don't change the measure of angles. So when we took this thing and we reflected it over, angle ABC, this angle, ended up being right there. It was this angle. And then when we dilated it, this angle ended up being this angle. Now, I don't know what the measure of that angle is. It looks like it's around 90 degrees, maybe a little bit bigger. Let's just say it was 90. If this was 90, then this is 90. And if this is 90, then this is 90. So those two angles are equal. These two things are trying to suck you into the idea that, I don't know, somehow I dilated this one by a factor of 1/2 to get this one. Now, by the way, there's nothing up here that says we dilated by 1/2, but you know, it looks like it could be. And therefore, somehow the angle shrunk down to 1/2 as well. Now, that would be crazy. Think about this just for a minute. If you took a triangle and you dilated it by a factor of 1/2, and all the angles got smaller by a factor of 1/2, then the angles of that triangle would sum to 90 instead of summing to 180. And we know from years of experience in geometry that the sum of the three angles of any triangle of any size is always 180, right? So it wouldn't make sense that under a dilation, the angles would change by that dilation constant. That just doesn't make sense. All right. So let's move on. Let's go back to blue. Is that our last problem? No. A few more problems with dilations. January 2016, number 31. All right. Line L is mapped onto line M by a dilation centered at the origin. That's important. I'm going to circle that really quick. Dilation centered at the origin with a scale factor of 2, also important. The equation of line L is 3x minus y equals 4. Determine and state an equation for line M. All right, so to begin with, I want to get just a little bit of a better sense for the line that we're beginning with, and they had to be obnoxious, didn't they? They could have given it to us in y equals mx plus b form, but they didn't. They chose to write it as 3x minus y equals 4. I'm going to write that line right here. 3x minus y equals 4. I'm going to put this thing in y equals mx plus b form so we can talk about it a little bit more. If I threw the y on this side, right, it would be 3x is equal to y plus 4. And then if I subtracted the 4 from both sides, I'd get the line y equals 3x minus 4. So I want to be very clear, this isn't my answer in any way, shape, or form. That's just line L written in a way where I can actually get a sense for it. So really quickly, I'm going to sketch that line. I'm not going to make it amazingly accurate. 1, 2, 3, 4. But you know, it's a line with a slope that's positive, and it's got a y-intercept down here at -4. So that's line L. Now I'm going to take this thing and I'm going to dilate it by a factor of 2, by a scale factor of 2, using the origin as my center. Now it's really amazingly important. Now there's a lot of points that lie on this line, and every single one of them is going to now be twice as far from the origin as where they began, right? Including the y-intercept, right? So the y-intercept of the new line now has to be down here at -8, right? The original y-intercept is 4 units from the origin. When I dilate it by a factor of 2, it now has to be 8 units from the origin. But the image line also has to be parallel to this line, right? So I can actually draw the image line. Let me draw it again in red just to give it some contrast. So that's got to be line M. Well, what's the equation of line M? Well, I know its y-intercept, it's -8. And because M is parallel to L, and we know that parallel lines have the same slope of 3, then I can say that line M has the equation 3x minus 8. Boy, it'd be really tempting to be like, oh, let me multiply that by 2, that by 2, that by 2. No. In fact, again, a line that is dilated by a point, using a point that's not on the line, will produce a line that's parallel to it. It just so happens that we can figure out what the y-intercept is because it must be twice as far from the center of dilation as where the original y-intercept was. Let's do another problem that seems very similar to this, but in fact has a very subtle difference. June 2018, last June. Number 24, line MN is dilated by a scale factor of 2, centered at the point 0, 6. If line MN is represented by the equation y equals -3x plus 6, which equation can represent M prime N prime, the image of MN? So it seems like this question is nearly identical, with one huge difference. And it's not the fact that they were nice this time and gave it to us in y equals mx plus b form, but that is kind of nice. Let me sketch that really quick, right? So I've got, we're going to start off in red this time. I've got the line with a y-intercept of 6, 1, 2, 3, 4, 5, 6, good, and a negative slope this time. So this is my original line. I have no idea where points M and N are, but I know it's called line MN. All right, now I'm going to dilate that thing, but not with the center at the origin. My center is now the point 0, 6. And what's really critical about that, what's exceptionally important about that, is that that point lies on the line of dilation. So whether I dilate this by a factor of 2, a factor of 200, or a factor of 1/2, or a factor of 1/10 makes no difference. If I take this line and I stretch it out, it's the same line, right? So the really tricky thing about this question is the right answer is simply the original equation. And that's the case because the point, the center of dilation, lies on the line that we're dilating. Kind of cool. Let's move on from dilations, and at the same time, get a drink of lemonade. People love the lemonade, so do I. Here we go. Sugar, electrolytes, very tart, very tart. Can you imagine the first person who decided to be like, I'm gonna squeeze a bunch of lemons in some water and then add some sugar? All right, proof. You know, I bet when you think about geometry, and you think about that test that you're going to take on Friday, right, Friday morning, you're probably like, oh my God, I can't do geometry proof, right? Which is sad, because geometry proof is one of the most beautiful things that you'll ever learn in math. It's the ability to take ideas, right, little ideas, and build them into bigger ideas, right, and eventually prove things that you wouldn't know otherwise, okay? But I don't blame you. if you're kind of worried about proof. Even sometimes when I sit down and I look at a geometry proof, I get that little twinge of going, ooh, am I going to see how to do this proof? Am I going to see how to do it? All right. Well, we're not going to do any proof quite yet. I think that's going to come on the next slide or maybe even the one after that. What we're just going to talk about in this slide is how we can prove triangles are congruent. So when two triangles are congruent, then all their corresponding sides are congruent and all their corresponding angles are congruent. That gets summarized in what's called CPCTC, corresponding parts of congruent triangles are congruent. Again, we'll get back to that a little bit later when we do a couple proofs. But we don't need to know all of that to conclude that two triangles are congruent. In fact, if we know that two pairs of corresponding sides are congruent and the angle in between them, known as the included angle, is also congruent, then we can say the two triangles are congruent. Likewise, if we know that two pairs of angles are congruent, two corresponding pairs of angles are congruent, and the side between them is congruent, then we can say the triangles are congruent. If we know all three sides of one triangle are congruent to all three sides of the other, we can say the triangles are congruent. If two angles and a side not between them are congruent to two angles and a side not in between them, they're congruent. And finally, a very specialized one. If we've got two right triangles and the hypotenuses are equal and one pair of legs are equal / congruent, those right triangles are congruent, known as hypotenuse leg. All right, let's take a look at the first problem. August 2018. In the diagram below, AKS, NKC, AN, and SC are drawn such that AN is congruent to SC. I'm going to mark that right now on the diagram. AN is congruent to SC. Which additional statement is sufficient? This word means enough, right? Which statement is enough to prove that triangle KAN is congruent to triangle KSC by AAS? Hey, look, I'm going to be honest with you. I was doing this problem for the first time the other day, and I thought it was a faulty problem because I thought like multiple ones of these choices were correct. And that was because I read it too quickly. I thought it just said which additional statement is sufficient to prove that the two triangles were congruent. But specifically here, it wants us to prove them congruent by angle, angle, side. Angle, angle, side. A little bit irritating because it's actually kind of your fourth choice, if you will, but whatever. Now, before we kind of get into the four choices, let's just give a nod to the fact that we know that these two vertical angle pairs are congruent. Vertical angles are always congruent. So all we now need to know is either that angle A is congruent to angle S, or angle C is congruent to angle N. Right? That's all we need to know to have angle, angle, side. Because remember, we don't want the side to be in between the two angle pairs. It won't be. The two sides that we know are congruent are between these two angles and these two angles, and we know that these two are congruent. Well, it says AS and NC bisect each other. So these two segments cut each other in half. Now, that would be enough to know that the two triangles are congruent, but it would be enough to know that they're congruent by side, 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 or side, angle, side. All right, either one of those would work if we knew that these two segments bisected each other. All right, it says K is the midpoint of NC. So if K was the midpoint of NC, this one's kind of an interesting one. That would tell us that these two sides were congruent, and we'd have a side-side angle scenario. A side-side angle. That is actually never sufficient. Well, I shouldn't say never. That is generally not sufficient to prove that two triangles are congruent. All right, that's a side-side angle scenario. So I'm gonna get rid of that. That one's not right. All right, AS is perpendicular to CN. AS is perpendicular to CN. Well, if we knew that AS was perpendicular to CN, all that would tell me is that these two angles that we already knew were congruent are both right angles. In which case we would know that they were congruent. But we already know they're congruent because they're vertical angles. So that's not gonna help me at all. All right, so it's pretty much got to be number 4. AN is parallel to SC. Now, if we know AN is parallel to SC, that's going to tell us that this angle pair is congruent. Those are alternate interior angles. And it's also going to tell us that this one's congruent. Now, just keep in mind, okay, With this information, this last little piece, it would be sufficient. It would be enough to prove these two triangles are congruent by two different methods, angle-angle-side or angle-side-angle. All right, but it is certainly enough to prove them sufficient by angle-angle-side. We got an angle congruent to an angle congruent to an angle, sorry, and a side that's not in between them that are also congruent. Parallel lines, very important. June 2016, number 7. Two right triangles must be congruent. Must be congruent if which of the following, right? So let's kind of draw this out, okay? Two congruent triangles, right triangles. All right, so let's draw two right triangles that are as sort of identical as we can. All right, like that. We know they've got to have right angles, right? And it says, well, must they be congruent if an acute angle in each triangle is congruent? Well, let's say that this is congruent to this. Well, all we would know in that case is angle, 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 right? Now that would be enough, as we'll discuss a little bit later on, to know that these two triangles are similar to each other. But we could very easily have one of these triangles be much larger than the other. This could be a 90 and a 30 and a 90 and a 30, but you could have like a really tiny 90 and 30, right? And they'd have two congruent acute angles and two right angles, but yeah, not enough. All right, so delete and maybe just erase. All right, let's take a look at the next one. The lengths of the hypotenuses are equal. Well, that's not going to be enough. Now we have an angle congruent to an angle and a hypotenuse or a side congruent to a side. There's nothing except for hypotenuse leg that has only two pieces of information. And hypotenuse leg actually has three pieces of information because right triangles, hypotenuse, and leg, right? That's three. All right, so not that one either. And a little bit hard to get rid of these, but we can get rid of them pretty quick. The corresponding legs are congruent, all right? So these legs correspond, and these legs correspond. That's enough, right? Because now we have a side congruent to a side, an angle congruent to an angle, and a side congruent to a side, with the angle being in between the pairs of congruent sides. We could prove that these two triangles are now congruent by side angle side. Now be careful. Certainly, if two right triangles are congruent, they obviously have the same area because they're identical. But you could easily have two triangles that have the same area, two right triangles that have the same area, that aren't congruent, right? I mean, think about, for instance, if you had a triangle that had a base of 10 and a height of 2, it would have an area of 1/2 10 times 2, which would be 10. On the other hand, if I had one that had a base of 5 and a height of 4, we would have an area that was 1/2 of 4 times 5, which would also equal 10. So just because you've got two right triangles that have the same area certainly does not mean that they must be congruent. All right, let's keep going. I like this one. June 2016, number 19. Line segment EA is the perpendicular bisector, very important term, perpendicular bisector of ZT. And ZE and TE are drawn. Which conclusion cannot be proven? So this is actually a very, very important diagram. You should have seen this diagram a fair amount of times in your geometry class, right? And the reason why is it kind of gets into isosceles triangles, and here's what I mean. We're told that EA is the perpendicular bisector of ZT, which means two things. Number one, these two angles are right angles, and number two, these two sides are equal. But because these two sides are equal, and these two angles are equal, and this is a shared side, we can now say that this right triangle and this right triangle are congruent. And because these two right triangles are congruent, we can use CPCTC all over the place to conclude other things. Corresponding parts of congruent triangles are congruent. So for instance, EA bisects angle ZET. You bet it does, Because that angle and that angle must be identical. They're corresponding angles between these two identical right triangles, so you bet we can prove that. We're looking at what conclusion cannot be proven. Second one, triangle EZT is equilateral. Well, an equilateral triangle is one where all three sides are the same length. So this is the same length as this is the same length as this. Well, there's no reason that has to be the case, right? They maybe have drawn it to make it look that way, but we could easily have a very short side here, a perpendicular bisector here, and then something like this, right? That would still, that horrible picture, but this would still kind of fit the bill and clearly is not equilateral. Now, what there's no question about is that this is an isosceles triangle because this length is now equal to this length, CPCTC. But we certainly cannot prove that this triangle is equilateral. Let me just go through the last two because they review some important terminology. It says EA is a median of triangle EZT. Well, absolutely. A median is a line segment that's drawn from a vertex to the midpoint of the opposite side. Well, the plain fact is because EA bisects ZT, A must be the midpoint of ZT, and therefore EA must be a median of ZT, or of EZT. All right, angle Z is congruent to angle T. That's this angle and this angle. Well, these two angles, again, are corresponding parts of these two congruent right triangles, so you bet they have to be congruent to each other. And finally, August 2016, number 22. Given triangle ABE and triangle CBD, shown in the diagram below, DB is congruent to BE. Which statement is needed to prove that triangle ABE is congruent to triangle CBD using only side angle side congruent to side angle side? I love the fact that they had to throw this thing in here. They couldn't have just said side angle side. So again, what this implies is that they want to force us to use SAS. All right, now keep in mind they're talking about triangle ABE, which is this guy, right? And they're talking about triangle CBD, which is this one. I'm going to actually draw those two triangles separated from one another because it's going to help me see things better than when they overlap. That can be very confusing. So I'm going to draw ABE, and then I'm going to draw a triangle DBC, and I'm going to actually throw on some other points here, just for the heck of it. All right, so these are my two triangles at this point. All right, now what do I already know? Well, I know that DB is congruent to BE, so I know that this side is congruent to this side. I mean, I know they're in kind of funny locations, but whatever, right? BE is congruent to DB. All right, the other thing that I know, because these two triangles overlap, is that angle B is congruent to itself. That's called the reflexive property of equality. Now, the only way I can use side angle side is if somehow I can make AB congruent to BC. All right? I somehow have to have AB congruent to BC. Well, keep in mind, right, that we already know something. We already know that DB is congruent to BE. We already know that those two lengths are the same lengths. And in fact, we could then figure out that AB is the same length as BC if we knew that length AD was equal to length EC. Right? And that is choice 3, right? And in order to do the proof would actually kind of be a little bit complicated. We'd have to use, basically an addition proof, right? Where we did, this partitioning and we added up segments and the whole is the sum of the parts and all sorts of things like that. But at the end of the day, if we knew that AD was the same length as EC, then we could simply add AD to BD, and add EC to BE, which we already know are congruent, and then we know this whole length is congruent to this whole length, and we'd have side angle side. All right, let's move on. Quadrilaterals. All right, quadrilaterals are four-sided figures. Any figure that has four straight sides is known as a quadrilateral. But there are all sorts of special quadrilaterals, and they kind of have a hierarchy. So we're going to review some of that right now before we get into the problems concerning quadrilaterals, and I'm going to go back to blue for it. All right, so let's first talk about trapezoids. Okay, trapezoids are one of the more general quadrilaterals. A trapezoid is any quadrilateral that has at least one pair of parallel sides. So it could have one pair of parallel sides, as this picture shows, or it could have two pairs of parallel sides. Now, speaking about figures that have two pairs of parallel sides, well, those would be parallelograms. All right. Now, because a parallelogram has two pairs of parallel sides, both pairs of opposite sides are parallel, all parallelograms are also trapezoids. That can be confusing for students, all right? But it's a hierarchy. It's like saying, well, all humans are mammals, and all mammals are animals, and all animals are living creatures, right? I mean, it's just a hierarchy of one category sitting in another. Parallelograms are trapezoids. Okay, but parallelograms are defined as, it's a figure with opposite sides being parallel. But there are lots of ways to prove things are parallelograms because they have all sorts of other great properties. For instance, all right, sufficient to prove a parallelogram. Both pairs of opposite sides are parallel. That's just the definition, right? Or one pair is parallel and the same length. So if I knew that one pair of opposite sides were both parallel and the same length, I'd know I had a parallelogram. Both opposite pairs are equal in length. So if I know that's equal to that and that's equal to that, I know it's a parallelogram. And finally, a little weird, is that if I know in a quadrilateral that the diagonals bisect each other, they cut each other in half, then I also know it's a parallelogram. All right? That's kind of cool. Now, there's lots of special parallelograms. For example, a rhombus is a parallelogram. But parallelograms are not mentioned in the definition of a rhombus. A rhombus is simply a quadrilateral where all four sides are the same length. Now you might say to yourself, wait a second, I thought that was a square. Well, squares are rhombuses, or rhombi, as we like to call them in the biz. But we'll get to squares in a moment. Rhombuses are just any four-sided figure where all four sides are the same length. Now, how do you prove something's a rhombus? Well, the easiest way, or the most straightforward, is, hey, all four sides are the same length. Or, if you already know it's a parallelogram, if you're already knowing it's a parallelogram, and you have two consecutive sides, or two adjacent sides that are equal in length, then it must be a rhombus. Now again, try to think about why that makes sense. I mean, if I know it's a parallelogram, then I know that side's equal to its opposite side. But if I know that this side's congruent to this side, well then this side must be congruent to this side, which must be congruent to this side, which must be then congruent to this side. So it's a rhombus. And finally, and this one's really important, a parallelogram with one diagonal, a parallelogram with perpendicular diagonals. I skipped that one. That's the important one. So rhombuses are really cool. They're kind of unique in the parallelogram world in that their diagonals form right angles with each other. If I drew these two things in, we have right angles, okay? So that's enough to also know that we have a rhombus. If we know it's a parallelogram, and we know its diagonals are perpendicular, it's a rhombus. And finally, the last thing, there's a lot of things about rhombi, the last thing about rhombuses is that these diagonals actually bisect, they bisect the vertex angles of the rhombus. So if we have a parallelogram and we know that one of the diagonals does that bisecting, then it must also be a rhombus. Now, it's a little bit less important, but you never know when these things will come up. Now, maybe one of the first quadrilaterals you ever learned about was a rectangle, right? I mean, they're so easy, they're so simple. And what's a rectangle? Well, it's a quadrilateral with four right angles. How do we prove something's a rectangle? Well, if we've got a quadrilateral and we're able to prove it's got four right angles, it's a rectangle. But if we already know it's a parallelogram, and we've proven that it's got one right angle, it's got to be a rectangle. Likewise, if it's a parallelogram and its diagonals are the same length, it's got to be a rectangle. And again, that's a really kind of neat property of rectangles. Generally speaking, parallelograms have a longer diagonal and a shorter diagonal, unless they're rectangles. And in a rectangle, those two diagonals are the same length. And finally, the square. What appears to be the simplest of all quadrilaterals actually is probably the most complicated, right? A square is simply a combination, it's sort of the Venn diagram overlap between rhombuses and rectangles, right? Because a square has 4 congruent sides, so it's a rhombus, and it's got 4 right angles, so it's a rectangle. How do you prove something's a square? You prove it's got 4 equal sides and 4 right angles. Or you prove any combination of rectangle and rhombus conditions. So if I know it's a parallelogram with diagonals that are perpendicular, then it's a rhombus, and if they're the same length, it's a rectangle, and if they're both, it's a square. Doesn't that make sense? Okay, let's get into some problems. Woo! August 2018, number 26. In parallelogram ABCD, so right away, we're told it's a parallelogram. In parallelogram ABCD, shown below, the bisectors of angle ABC and DCB meet at E, a point on AD. If measure of angle A is 68 degrees, determine and state the measure of angle BEC. All right, that's 68 degrees, and I want that angle. So let's start working it. Okay, well, what are some of the properties of angles of a parallelogram? Well, one thing about parallelograms is that angles that are opposite in the parallelogram are congruent. So if angle A is 68 degrees, then angle BCD is also 68 degrees. This whole thing, right, is 68 degrees. But we're told that EC is the bisector of that angle, which means this angle must be 34 degrees. Now, the other thing we should know about angles in a parallelogram is that adjacent angles, not opposite angles, but adjacent angles are supplementary. They add up to 180 degrees. So if I do 180 degrees and I subtract 68 degrees, I'll get 112 degrees. That would be all of this, right? But again, I'm told that BE is a bisector of that angle, right? And since it's a bisector of that angle, I can take 112, I can divide it by 2, and that's going to give me, what, 56? 56 degrees, right? But that's great, because now I can take triangle BEC, I can add 56 and 34, I find that that's 90 degrees. These two angles add up to 90. If I subtract that from 180, I probably don't even need that. Then I find my missing angle, which happens to be 90 degrees. Isn't that kind of cool? So the missing angle, what we wanted, was 90 degrees. Perpendicularity. We're not getting close to hour 2, are we?
34.
Oh, okay. We got plenty of time. Sorry, I don't know. I lose track of time when I'm absorbed in geometry. What can I say? June 2015. Number 13. Quadrilateral ABCD. Now this is important. Quadrilateral ABCD. Not parallelogram, not rhombus. All we know is this is just a generic 4-sided figure at this point. Quadrilateral ABCD has diagonals AC and BD. Of course it does. Which information is not sufficient to prove that ABCD is a parallelogram? All right, let's take a look at this. Now, I'm going to draw a quadrilateral that looks like a generic parallelogram. A, B, C, D. I'm going to draw in its diagonals. All right. And now let's take a look at each one of these choices. Now this can be a little tricky, okay? Because every one of these 4 choices is going to be true about this figure. The question is it enough information to know that it's a parallelogram? So the first thing, AC and BD bisect each other. Yes. When the two diagonals of a quadrilateral bisect each other, it must be a parallelogram. So absolutely. But we're looking for what's not sufficient. The next one says AB is congruent to CD and BC is congruent to AD. In other words, we have two pairs of opposite congruent sides. Indeed, that is enough to prove it's a parallelogram. All right, AB is congruent to CD and AB is parallel to CD. So if I've got a pair of sides that is both the same length, right, a pair of sides that's both the same length and parallel to each other, it forms a parallelogram. Yeah, which means the correct choice is number 4. But let's take a look at why this isn't enough, because it sure seems like it should be. This one says AB is congruent to CD and BC is parallel to AD. And you might say to yourself, but that's true. On a parallelogram, this is true. Yeah, it is true. But just because it's true on a parallelogram doesn't mean it's enough to prove something's a parallelogram. So let me show you a figure for which I can make two sides congruent and the other two sides parallel, and it's not a parallelogram. In fact, what we used to call an isosceles trapezoid would exactly fit this description. In other words, if I had a figure like this, A, B, C, D, where A, B, and CD were congruent, and BC was parallel to AD, that's not a parallelogram, right? That's not enough. So it's really quite critical in a question like this to know all the different ways that you have to prove something is a parallelogram. August 2015, number 1. A parallelogram must be a rectangle when it's what, right? So we're starting in this problem with a parallelogram, all right? What makes it a rectangle? So in a problem like this, what I like to do is I like to actually draw a generic parallelogram. I don't draw a rectangle. I draw a generic parallelogram, all right? There's some stuff in here about diagonals, so I might as well draw the diagonals in. And it says, okay, well, number 1, diagonals are perpendicular. Well, if I made these two diagonals perpendicular, which they aren't right now, all right, what I would get is I'd get a rhombus. I wouldn't necessarily get a rectangle. So no, that's not enough. The diagonals are congruent. Well, right now we've got a shorter diagonal and we've got a longer diagonal, okay? And that is, in fact, enough to make it a rectangle. So what makes something a rectangle is literally when I take those two diagonals and I suddenly make them equal, yeah, now that's a rectangle. This is my correct answer. Let's take a look at the last two. Opposite sides are parallel. Well, that's true for every parallelogram, including a rectangle, by the way. But it's not enough to prove a parallelogram is a rectangle because all parallelograms have opposite sides that are parallel. And the same is true for number 4. Opposite sides are congruent. That's true of all parallelograms. It's true of all of them. So it's certainly not enough to prove that it's a rectangle. The big one with rectangles are congruent diagonals, diagonals that are the same length. June 2018, number 13. The diagram below shows parallelogram ABCD with diagonals AC and BD intersecting at E. What additional information is sufficient to prove that parallelogram ABCD is also a rhombus? All right, so this is a problem that is structured very similar to the last one, except they gave you the picture. And again, it's almost a little unfortunate that they gave you the picture, because what I would prefer is that I've got some generic parallelogram. Well, maybe I should label it the same way as this one. I don't think it really matters. A, B, C, D, E. Right? So what makes this into a rhombus? Well, BD bisects AC. True of all parallelograms. All parallelograms have diagonals that bisect each other. That's not going to make it a rhombus. AB is parallel to CD. AB is parallel to CD. Well, again, true of absolutely every parallelogram. That's just opposite sides being parallel. AC is congruent to BD. AC is congruent to BD. That's the rectangle condition. The two diagonals are the same length. Finally, choice 4, AC is perpendicular to BD. There's our winner. All right, so when we have parallelograms, if the diagonals are the same length, we get rectangles. If the diagonals are perpendicular, we get rhombuses. If both of them are true, we get squares. Kind of like me. I have perpendicular diagonals and equal length diagonals. Okay, last problem. January 2017. All right, in the diagram below, if triangle ABE is congruent to triangle CDF, and AEFC is drawn, then it could be proven that quadrilateral ABCD is a which, right? So right now they're saying to me, oh, all right, like ABE, this triangle, is congruent to CDF. All right, and that's enough to prove which one of these. All right, I like this question because I immediately know this is the answer. All right, and let me explain why I immediately know that's the answer. Just by using logic, and here's what I mean. All right, if I had enough information to prove that this thing was a square, I could also prove that it's a rectangle, because all rectangles are squares. If I had enough information to prove it's a square, I could also prove it's a rhombus, because all squares are rhombuses. But if I had enough information to prove it's a square, a rhombus, and a rectangle, I'd have enough information to prove it's a parallelogram, because all of the other three are also parallelograms. The plain fact is, if I can prove it's any one of the other three, then I can certainly prove it's a parallelogram, because they're all parallelograms. That's got to be the right choice. Now, here's what they really wanted you to do. All right, what they really wanted you to do was say, oh, well, these two triangles are congruent, and because of that, CPCTC, congruent parts of corresponding parts of congruent triangles are congruent. For instance, this must be the same length as this, because they're corresponding parts of those two congruent triangles. But likewise, this angle would have to be congruent to that angle, because corresponding parts of congruent triangles are congruent. Now, why is that important? Well, if this angle is congruent to this angle, it would mean that alternate interior angles are congruent, and that would mean that this side is parallel to that side. And therefore, we would have two sides, two opposite sides that are both the same length and parallel, which would give us a parallelogram, right? That's what we would know. But we could also just know it's that way because this thing, right, all three of the others are this one. So it's got to be that. All right. Whew, we're moving along. Da 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 da. All right. Now, we could literally have spent all 3 hours just doing really long proof. But let's get down to brass tacks, okay? On the Geometry Regents exam, right, it is very likely that the last problem, the part 4 problem, is going to be a 6-point geometry proof. The two that I'm going to do in just a moment are both that way, all right? And geometry proof has lots of different flavors and lots of different things that can be involved, partitioning, different theorems, ASA, SAS, etc., etc. Most of the long proofs that we've been seeing have involved quadrilaterals and congruent triangles all kind of together, all right? Now watch, Friday, that won't be the case. But the plain fact is that is generally what happens with these, okay? So we're just going to do 2 of these long form proofs. That is absolutely it. Otherwise, we would have no time for trig and similarity and measurement and constructions and circles. We got some material left. Let's take a look at August 2015, number 35. In the diagram of parallelogram ABCD, this is amazingly important. That's a given. In the diagram of parallelogram ABCD below, BE is perpendicular to CED, DF is perpendicular to BFC, and CE is congruent to CF. Prove that ABCD is a rhombus. All right, so let's get a strategy almost always, before I do a proof, I know how I'm going to get through it. I know every step I'm going to take before I ever write a single one down, or at least I'm going to have a general strategy. So first, let's kind of start backwards, right? I need to prove this thing's a rhombus, but I already know it's a parallelogram. Now, generally speaking with rhombuses, most of the time what you're looking to do is prove that their diagonals are perpendicular to each other. But there are no diagonals drawn in this picture, so I don't really want to introduce that. But there's another way to prove that a parallelogram is a rhombus, and that's by proving that two adjacent sides, two sides that touch each other, have the same length. And probably the two that I'm going to be looking to try to get is side BC being the same length as side CD. So if I can get BC and CD to be the same length, somehow if I can prove that, then this parallelogram will have to be a rhombus. Well, how can I get BC and CD to be the same length? Well, I can do that if somehow I can prove that this triangle, triangle BEC, is congruent to triangle CFD. If I can prove that those two triangles are congruent, then I can say, using CP/CTC, that BC is congruent to CD, and then using that fact and the fact that it's a parallelogram, I can then say that this thing is a rhombus. So can I figure out that this triangle is congruent somehow to this triangle? Well, let's see what they've told me. So at this point, I'm going to start to bring in all of this kind of stuff over here. Well, they tell me that BE is perpendicular to CED. That means that's a right angle. They tell me that DF is perpendicular to BFC. That means that's a right angle. Oh, that's kind of helpful, right? I also know, by the way, that they share angle C. Right? That's going to be a shared angle between these two right triangles. And again, the two right triangles I'm talking about, just in case you're not absolutely certain about it, is this one, DFC, and this one, BCE. Now right now, right, I know I've got these two right angles that are congruent. I've also got these two shared angles that are congruent. But they also tell me that CE is congruent to CF, that this is the same as that. That's it, right? That means this triangle and this triangle are going to be congruent by angle, side, angle, right? So I can now prove these two triangles are congruent by angle, side, angle, which is then going to allow me to conclude that BC is congruent to CD by CP/CTC, which is then going to allow me to conclude that this thing is a rhombus because it's a parallelogram with two adjacent sides that are congruent. I just have to get it all written down, right? And it's a little ugly. It really is, and it's a little long. I debate whether or not it's even worth taking the time, given that I can't even find where the proof is. Still looking. Here it is. Look at this. Look at how long this is, and it scrolls onto the back of the sheet. Anyway, but let's start to take a look at it. All right, so we've got the whole statement reason thing. It's going to be really helpful if I could keep that in the view, but there probably is no way to do it. Right, statement reason 1. Right, so we would want something like BE is perpendicular to CED and DF is perpendicular to BFC. Those are given, right? No points given for writing down the givens, by the way. Oh, I'll write down the givens. They'll give me 1 point. No, they won't. All right, that means that angle DFC and angle, BEC are, are right angles. Here we could say definition of perpendicular lines. Then we could say that angle DFC is congruent to angle BEC. All right angles are congruent. That's our first angle pair, by the way. I just almost tripped over my own feet. All right, that's our first angle pair. Then I could say, right, that angle C is congruent to itself. Angle C is congruent to angle C. Anytime I say something is congruent to itself, it's called the reflexive property. Right? Then I can say that CE is congruent to CF because they told me that. That was a given. Now, even though I've listed them in the order of angle, angle, side, it's actually angle, side, angle, right? And we can see that in the diagram that we've kind of scoped out, right? We have an angle equal to an angle, a side equal to a side, an angle equal to an angle. So I can conclude now, well, I'm almost out of space. I can conclude, I don't know why I had to put those, there we go. I don't need parentheses around that. Delete. I can now conclude that triangle BEC is congruent to triangle DFC by angle, side, angle. I can now say that side BC is congruent to side DC because corresponding parts of congruent triangles are congruent. And finally, the coup de grace, 8. Well, actually, I never said it was a parallelogram. I gotta say that. Shoot, ABCD is a parallelogram. Given. And now my ninth line, which I can barely fit in, ABCD is a rhombus. Why? Because it is a parallelogram with two congruent adjacent, that's very important, adjacent sides. I think if you said two congruent consecutive sides, that would be okay too. Now again, I had worked out all the logic of this to begin with, right? And the logic was essentially, hey, you know, I've got those two right angles that are equal. I've got that shared angle pair that's equal. I've got those two sides that are equal that they told me, and that's going to allow me to conclude that this right triangle is congruent to this one. Because those two are congruent, I can then say that this, the hypotenuse of that one right triangle, is congruent to this, the hypotenuse of the other one, by CPCTC. Now, because those are two adjacent sides of a parallelogram, I can now conclude that it's a rhombus. Ba-ba-ba-ba. And the next proof is even longer. All right, maybe we'll just outline how to do that again in the interest of time. I know that for many of you, this is probably all you want me to do. But the plain fact is, right, a really long proof like this is going to be worth, at most, 6 points. 6 points. Now, it doesn't mean you couldn't have a 6-point long proof and maybe like a 2-point shortish proof or a 4-point maybe semi-long proof, but that's pretty rare that they do that. Pretty rare, all right? So let's take a look at the next problem, again 35 being the last problem on the test, and let's talk about how we would go about doing this proof. I'm not sure that we'll write it all the way out, but maybe we'll just take a look at sort of the logical flow and where you'd go on it. 35 from January 2017. All right, in quadrilateral ABCD, I'm going to just pause for a moment. See, this time we don't know it's a parallelogram. This time we're just told it's a quadrilateral. But we know that AB, I'm going to draw this up, is congruent to CD. And we also know that AB is parallel to CD. BF and DE are perpendicular to diagonal AC at points F and E. All right. I think we have it back.
Yeah.
We have our audio back. Sorry about that. Sometimes things like that just happen. It's okay. I saw it happen on the Daily Show the other night. That's not true. That's a complete lie. They have like mics everywhere. But yeah, we've got a mic. You know, I'm wired on coffee and a mic. Anyway, I'm going to take a drink of lemonade, then we're going to get back to this proof.
Oh, you know what? We're at 57.
Oh my goodness. We're actually at the end of hour 2. That's crazy and a little distressing. Okay, so what we're going to do, we're going to break right now, and then we're going to come back for the last hour. So we'll see you just in a bit, and then we're going to talk about the logic of this proof, and then we're moving on from proof. All right, see you in just a bit.